And let's talk about Chapter 11, which is about the derivative, but it actually starts off talking about limits. Now, in 1530, you learned about how to deal with what are called static situations. Situations that occur in a single moment in time. What is the revenue when 100 items are sold? You've got a revenue equation. You plug in X equals 100 for the number of items sold and find out how many dollars you took in for doing that.
Mine doesn't say that.
Everything that's on my slides may not be on your notes. Okay, every single thing that's on the slides is not on the notes, or it will be 145 pages long. Okay, stuff that's important is in the notes. This is just background, things to get class going. So, how much interest is earned on a savings account deposit or a CD in 3 years? So you plug out what the interest rate is and how much you put in the bank and all the variables and find out how much interest you paid on it. What's the equilibrium price? Where does supply equal demand? Where does cost equal revenue? Okay, so you either solve it algebraically by taking your revenue equation equals your cost equation, solve for X, and then plug in to see what the cost and revenue for that number of items is to break even. Okay, those are things out of 1630, finite. In this class, things are not exactly the same kind of problem, but they're a far more realistic kind of problem. In this class, we're going to deal with dynamic situations, situations that are changing. At what rate is the demand for a product changing? Is it increasing? Is it decreasing? How fast is it increasing or decreasing? How fast is the car moving after 2 hours? When does the growth of a population begin to slow down? So the techniques of calculus are going to let us answer those kinds of questions, and those kinds of questions deal with something called rates of change. In 1630, we talked about slope. What is the slope of a line? And the problem you saw me doing in Shelby at the first of this class, they were reviewing the idea of slope. What is the slope of a linear equation? But in calculus, we're going to deal with more than the slope of a line. We're going to deal with the rate of change of a curve at a given point. Now, when you did slope of a line, you have 2 points. But when you're talking about the slope of a curve, we're going to talk about the slope of a curve at a single point, which, if you don't have 2 points, you're probably sitting there saying that you can't do change in y over change in x if y doesn't change and x doesn't change. And that's true. What calculus does is it lets us have a formula for the slope of a curve regardless of what point we choose. But we're going to start by learning how to calculate that slope by actually looking at 2 points really, really close to the point we're really interested in. Okay? And the idea underlying what I'm talking about is the concept of a limit. And we're going to start by studying limits. But before I talk too much about the mathematical part of what we're talking about, in this country, U.S. citizens are all about their personal space. Not everybody in here knows what your personal space is. Some people need more than others. But everybody has this little invisible line around them that you don't want anybody getting inside that circle. When they start getting too close, you're like, okay, back up. Don't be getting in my face. Back up. You're in my personal space now. Move back. Now, in Europe, they're not really that big. They're like all up in each other's face. They're very emotional, passionate, loud people sometimes, especially if you're talking about France and Italy and Spain. If you're in the Orient, personal space is way over here. I mean, they have raised personal space to make fine art. It's a very, very different culture. We all have different amounts of personal space that we need. Points on the line have personal space too. But their personal space is really, 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 really small, so they're kind of European. They'll let you get really, really close before they say, You're done. No closer. Okay? So you're going to imagine that you're a point on a line, and you've got your personal space, and you've got other points that are in front of you on that line, or on that curve, because it doesn't have to be a line. There's other points that are in front of you on that curve, but there's also other points behind you on that curve. And those other points can become the points to calculate a slope. And as those points get closer and closer to where you are, their slope becomes closer and closer and closer to your rate of change at your own single one individual point. Okay? So we're going to kind of look at this with that kind of an outlook, but we're going to start introducing a little bit of math to it. So for example, we have a function f of x equals x squared. What we want to do is we want to investigate what happens to f of x, not to x itself, but what happens to f of x and its rate of change as x becomes very, very close to, but is not allowed to be equal to 2. Okay? So let's suppose we have x is 1.9. Is that close to 2? Yeah. And at 1.9, the value of the function is 3.61, which we did right before class started. So if f of x equals x squared, is 1.99 closer to 2 than 1.9 is? Yeah. So then we square 1.99 because that's what the function says to do. And 1.99 squared is 3.9601. 1.999 is even closer than 1.99 was. And when you square 1.999, we get 3.996001. So then we move yet one step closer. 1.9999. 1 and 9,999 10,000ths. I'm 1/10,000th away from 2. 2 is getting uncomfortable. Okay? If you square 1.9999, you get 3.99996000001. Okay? Now, in case you're having trouble picturing this, we're going to do a little interactive demonstration here, and I need a volunteer. I am 2. Who wants to volunteer to be a point close to 2? You're not going to start out real close to it, I'll tell you. Somebody's willing to stand up back there in the middle of the room. Thank you. You are 2.1. Okay? How far is it from me to you?
Quite a distance.
But it's 1/10. Okay? It is quite a distance in this room because we're under a microscope here. But you and I are 1/10 of a unit apart. Okay? What is his function value? What is f of 2.1? Let's make it easier for y'all to read because that light's kind of bright and you need to be able to read it now. Does that help? A little bit? That might be better still. Okay. Notice that as he got closer and closer to me, his function value got closer and closer to my value. Okay? And if we had gone from the other direction, 3.61, 3.9601, 3.996001, 3.99960001. Okay? the limit as x approaches is not necessarily equal to 2, for f of x equals x squared is 4. Now, at this point, the question in your mind ought to be, why did you go through all of that when all you had to do was square 2 to begin with? Because that was the question I had in my mind. You're going to have a lot of trouble to do something that's obvious. You could just plug in 2 while you're going so much trouble. Okay, so that's a reasonable question to have. Before I try to answer that question, let me point out to you that nobody likes to do this with pencil and paper by hand. It's a lot of annoyance to have to do all this multiplication. Basically, it's just arithmetic. We can build that table on the calculator. But just to get some language out of the way, the phrase x approaches 2 from the left, meaning from the negative side of 2, numbers less than 2, left, less than. From numbers less than 2, x approaches 2 from the left is written x with an arrow, the arrow being red, approaches the number 2, and then the little negative sign is up in the air after the 2 to say that it is approaching 2 from the negative side of 2, from the back side of 2. Okay? That's called a one-sided limit. It's approaching from one direction. Similarly, if you approach x from the positive side of 2, or the right of 2, because when you go to the right of something, you go to bigger numbers, they're positive numbers, that's written as x approaches 2 from the positive side. Okay? Those expressions are used to write one-sided limits. The limit from the left as x approaches 2 from the negative direction is written limit, L-I-M, and then x, arrow 2 with a little negative as the, kind of like an exponent or a superscript, and that is read as the limit as x approaches 2 from the negative side, and it equals 4 because if you come from 0 and you slide along this graph of the function, you see that as 0 approaches 2, that your y values, your f of x values increase, and when you get really, really close to 2, the function values get really, really, really close to 4. Okay? And by the same token, if I'm approaching from the right side or from the positive side, I start out with really, really large f of x values, but as I get closer and closer and closer to 2, as x approaches 2 from the positive side, the limit of x approaching 2 from the positive side of f of x is x squared is equal to 4. Now what we're going to do at some point in the future is we're going to have the points approach x from both sides, and as they approach x from both sides, we'll actually have 2 points to calculate that slope. So what we're really doing is we're not trying to sneak up on the x squared is 2 squared is 4. What we're really trying to do is we're trying to sneak up on the slope where x is 2 while we still have 2 points. And as those little points get really, really close to the point we're interested in, then the slope between those 2 really, really close points is going to be really close to the slope of the function at 2. That's eventually where we're going. That's a pretty fuzzy concept right now, I'm sure.
Can you back up one slide just for a second?
Sure. You need this one?
I got that.
Okay. Now, a two-sided limit, because remember those other two, I said they're one-sided because it's either approaching from the negative or from the positive. A two-sided limit just doesn't have any signs. It says you're approaching from both sides at the same time. And that two-sided limit exists only if both of the one-sided limits exist, and ours did, and they are the same. In other words, I can't sneak up on 2 from the left and get closer and closer to a value of 5, and then try to sneak up on 2 from the right and get closer and closer to a value of 1, because then they're not going to come together and they're not going to meet at the same value. So it can't be this way. That limit doesn't exist if they're going to miss each other at the point you're trying to approach. They have to actually come together at that point. Okay? So they have to be equal. Now, this is the math language. This is straight out of the book. But I want to put it in English because we understand English and most of us don't speak math. So I want to put it in context. So, the definition of a limit describes what happens to f of x when x is near but not equal to the value of a, whichever a is. A is the value of x that we're investigating. Okay? It isn't affected by how or even whether f of a is defined. In other words, it can approach 2 from both sides, and as long as you're closing in on the same function value, the actual value of 2 doesn't even have to be between those 2 points. Function value of 2 may be way up here, or it may not exist at all. So f of 2 didn't even have to be defined for us to be able to find the limit as x approached 2 from either side. F of 2 might not have even been defined. The definition implies that the function values cannot approach 2 different numbers. That's the thing to keep in mind. The right-hand limit must equal the left-hand limit, or the limit doesn't exist. Okay? If the limit does exist, it's unique because they both have to be coming together from both sides on the same number.
Can you go back to that just a second?
This one? Okay.
That's fine.
Okay. So this is our second example. This says find the limit as x approaches 2 of g of x, but g of x is an x squared this time. This time g of x is x cubed minus 2x squared over x minus 2. A much, much uglier function. Now, before we investigate it looking at a graph, I think we're going to investigate it with a table. So let's get your calculator and let's try the table so that you can see. You can go through these pretty quickly. You don't actually have to slog through all this number business yourself. Now, it's already done here. So what I'm going to do is I'm going to escape from this and get the calculator so I can go through it with you. And the only thing I'm going to do while I'm here is clear off the home screen and hit my y equals and clear that out and put in this function. So the function itself is, the numerator is x raised to the third, subtract 2x and either raise to the second or hit your squared button. That's the numerator. Make sure it's in parentheses. Divided by, the denominator was x minus 2, and it needs to also be in parentheses. Now, for those of you that have a TI-84, you may or may not need those parentheses because the TI-84 will actually build a fraction for you. but I think if you put the parentheses in, it won't hurt. It never hurts to put those parentheses in. So now I'm going to take leave of this for a second, so I can make this a lot bigger. So you'll be able to see it better, even though I may have to move it around a little bit. And the next thing that I need to do is I need to set up the table the way that I want the table to come out. So I'm going to hit the second button and then the window button to go to table setup. And the only thing that, it does not make any difference whatsoever what that says. You can ignore where it says table start. I want you to arrow down, and I want you to put your cursor on the ask button for the independent variable. That's X. And hit enter. So I want your screen to look just like that one, except it doesn't matter what table start or what delta table says. The numbers in those top two don't make any difference. Just make sure that independent is ask and dependent is auto. Once you get that done, hit your second button and the graph button. And I've got a bunch of numbers that were already in my table. If yours has some numbers, just hit your delete button until they all go away. Because we want to start this table out the way that we want it. Okay? I'm going to pop back to the PowerPoint for a second. We're trying to find the limit as x approaches 2, which is exactly what we did a few minutes ago, except we're using an easier function. We're using f of x equals x squared. Okay? So we're going to use the calculator to build the table. We're going to start by sneaking up on 2 from the negative side. So we're going to start with 1.9. And lo and behold, we get 3.61 again. So then we'll say, okay, let's get a little closer. 1.99, 3.9601, 1.999, 3.996, 1.12349s, 3.9996. And what you're going to see next is going to bother you a little bit. So hang on. 1, 2, 3, 4, 5 nines. That's X. 1.99999. When you hit enter, it changes it to a 2. The reason it changes it to a 2 is because it's not that close to 2. I could put 6, 7, 8, 9, 10 nines out there and it's still not 2. It's just really close to 2. If you put your cursor back up on that 2, it tells you what it really is. The reason it changed it to 2 is because it can't give you more than 6 digits or 6 characters worth of information in the table. Okay? So that's why it's telling you that it's 2, even though it is 1.99999. And if you take your arrow over to the 4, that's not really 4. That's just really, really close to 4. Okay? And in fact, just for the sake of argument, I'm going to even go one more. 1.12345 nines. And that's really what there is. What's there is 1 followed by 6 nines after the decimal, and that 4 is 3.999996. Pretty darn close to 4. Okay? So as I sneak up on 2 for that function from the negative side of 2, what's the function value approaching? 4. Okay, let's sneak up from the other side. We'll start out at 2.1. Is 4.41 very close to 4? Not really. It would round to 4, but that's still quite a bit of difference. But if I go 2.01, that's pretty close to 4. 4.0401 and 2.12 zeros and then 1. 4.004. .00004. Guess what's going to happen when I put in that fourth zero? It's going to tell me it's 2, but it's not. And it's going to tell me that that's 4, but it's not. It's really close to 4, though. And if I add one more zero, I get even closer to 4. Now, I could keep on doing that, but all that's going to happen is eventually I'm going to have so many zeros, it's going to say 4.000000, and that's still not really 4 because somewhere out there there's going to be another 4 at the very end. It's just going to keep on adding zeros. So as I use that new function and I approach 2 from the left and I approach 2 from the right, as x approaches 2, what does g of x approach? 4. Okay? Now here's the thing that's troublesome about that. The limit of g of x as x approaches 2 is 4. What is g of 2? Is it? What is g of 2? 2 minus 2 in the denominator is 0. G of x is not defined at x equals 2. G of x does not exist at x equals 2. But the limit for g of x as x approaches 2 does exist, and it's 4. Okay? So the value that that x you're trying to approach, your function at that value doesn't even have to exist, but you can still get the limit as you approach that number. That's the point. Now this is the algebraic method. This is one of the few places we're going to use some algebra here. If we factored the numerator, what happens is that x cubed minus 2x squared actually factors to x squared times x minus 2. And the x minus 2 in the numerator and denominator cancel. So g of x is actually equivalent to x squared as long as you don't let x be 2. That's the one place where they part company. X squared can have x equals 2, but g of x can't have 2 as any of its domain values. Okay? Now, we can also look at a window on the graphing calculator. And here again, I'm going to actually walk through this with you. So what we're going to do is we're going to go to the Zoom menu, which is right in the middle of those blue buttons. and we're going to go to zoom decimal. So we're going to arrow down to number 4 and hit enter. And there's the graph that you see. But since the part of the graph we're really interested in is where x is equal to 2, well, that happens in the first quadrant. So in order to have just a bigger viewing window of the first quadrant, what I'm going to do is I'm going to go to the window and I'm just going to set the minimum x value to be 0. And then go down and set the minimum y value to be 0. And then I'm going to do one other thing because I would like to see a little bit higher up on the y-axis. So I'm going to take that y-max of 3.1 and I'm going to multiply it by 3. Just hit your multiplication button and 3. You can size your window this way just by doing an arithmetic, multiplication, or division, or adding and subtracting right on this window. And you can adjust your window from here. So when I hit enter, it's going to actually go from 0 to 4.7 on the x direction, and it's going to go from 0 to 9.3 on the y direction. And you're sitting there saying, well, what is special about these decimal numbers? Why don't you just go from 0 to 5 and 0 to 10? Well, there's something happens on your calculator when it's plotting a graph. What it does is it actually goes to the value of a pixel on the screen, and it calculates the position of those pixels. And if it gets to a pixel where the x value is 2, then on this window it's going to hit exactly x equals 2. You're going to be able to see what the value on the graph is for x equals 2. So once I've done that, the other thing that I'm going to do is I'm going to hit my mode button. And somebody's been playing with the calculator, but the radian and degrees doesn't really matter to me. What I want us to change is I want us to put this calculator in dot mode. So put your calculator in dot mode. Just hit mode and go down to where it says connected and then dot and go highlight dot. I don't want it to try to connect up all the pixels. Because what it'll do is it'll get a number here, and if 2's in there and it doesn't exist, it'll just connect them up with a straight line. So, okay, I'm going to put 1 in there anyway. But I want it to actually do the points. And now you can hit graph. And I want you to look very, very carefully at that screen and tell me what you see that you think is a little bit unusual. There's a hole. Where is that hole? It's where x is equal to 2 and y is equal to 4. Okay? But the limit, and I'm going to trace here. I'm going to go from the positive side first. I'm going to go way up above, and I'm going to go from 3 down closer and closer to 2. And notice that y is getting smaller and smaller and smaller and smaller and smaller and smaller and smaller. So I'm only 5/100ths from 2 right now, and it's at 4.2025. But if I go one more, I fell in the hole. Okay? And if I start out at x equals 0, and all I'm going to do right now is just type a 0 to tell it that's where I want it to start. And then I'm going to go to the right. I'm going to do the same thing. I'm sneaking up on 2 from the negative side. Getting pretty close. I'm only 5/100ths away, and I'm at 3.8025. But if I go one more, I fall in the hole. So the limit from the left was 4. The limit from the right was 4. But g of 2, not defined. The limit exists, but the function doesn't at x equals 2. Okay? Now, you can do this from the calculate menu and have it start anywhere you want it to. You can actually go to the calculate menu, and I'll pop that calculator back up here for just a second and show you. If I wanted just simply to go and see where x is equal to 2, I just go second, trace, and choose value, and hit enter and say let x be 2, and it's going to show me the hole. Even if I can't see it on the graph right there, it's going to tell me there's a hole. X cannot be 2. I can go over here to calculate and choose value and say let x be 1.9999999, and it gives me a value, and it says it's 4. That's because it rounds to 4, because look how many 9s I put in there. Okay? In fact, if I quit and go back to the home screen, and I say, for this I'm going to have to move the calculator up a little bit, or a whole lot. If I go alpha, and down here the number 1 key, to print out a y, and I say what's y, it tells me it's 4. Because it's got so many digits, so many zeros between that 3 point and that big long number. It's got so many digits it can't show me all the digits. I can even ask it, what is 1.9999999 squared? Now it'll show me that, but the graph screen thought it was 4, and that's what it's going to tell me. So my caution to you here is be careful interpreting what your calculator tells you. It will tell you the truth within limitations of its ability to show it to you on the screen. It knows how to do all the arithmetic more than you and I could do, faster than you and I could do, but it will round off answers if you aren't careful. You don't know that that's what it's doing. You know that 1.99999999999 squared isn't 4. It's 3 point and a whole bunch of 9s, but it's not 4. Okay? So, a limit can be found 3 ways. Algebraically, which generally means you have to factor and do some canceling or something like that. Using a graph that you can draw with a graphing calculator, which is handy. Or using a table, which you can write out by hand, or you can make it with a graphing calculator, which is much faster.
So on page 3, what were the answers to the blanks that fill in?
Let me go back and look at the notes so I can tell you exactly what it's supposed to be. I think I said it, but I don't remember exactly what page 3 says. Okay. G of 2 is undefined because you can't divide by 0. The limit as x approaches 2 from the negative side of g of x is 4. The limit as x approaches 2 from the positive side of g of x is 4. But g of 2 is undefined. Okay? So now we're going to work on example 3. H of x, well again, you're going to notice that we're using x squared a lot simply because it's easy to do the math. Okay? That's why I'm picking functions that have x squared in them. It's because it's easy to do the math. We don't have to worry about complicating the arithmetic. We're trying to understand an idea. So we're using the limit as x approaches 2 of h of x, and h of x is equal to x squared as long as x is not 2. If x is 2, h of x is equal to 1. This is a piecewise function. Okay? It has different rules for different parts of its domain. Everything in its domain, all x values except for 2, you square them. But if you've got 2, you don't square it, it's 1. Okay? What do you think the limit of h of x is as x approaches 2, based on what you've already seen? Come on 2 from the negative side and you square it, what do you get? Closer and closer and closer and closer to 4. If you get from the upper side of 2, you come from 3 down to 2 and 2.1 and 2.01 and 2.001 and 2.00001, you're getting closer and closer to 4. When you get to 2, what's h of x? 1. But the limit is 4. The value of the function and the limit of the function do not have to be the same. Okay? So this limit, just like the others, would have been 4. Even though h of 2 is 1, as you approach 2 from either side, h of numbers close to 2 is 4. The only requirement for a limit to exist is that you approach the number from the negative and from the positive and get the same output, the same function value. Then the limit exists and it has that number, regardless of whether that's the number that you're trying to sneak up on's value or not. Okay? Here's one that's not x squared, but it's still not hard. First of all, what is the value of f of x at x equals negative 2? It's undefined, right? Because 2 times negative 2 is negative 4, and negative 4 plus 4 is 0, so f of x would be undefined when x is equal to negative 2. Not happening. But can we sneak up on negative 2 by going to the left of negative 2, which in this case, since we're going to the left of a negative number, that's going to be like negative 3 point, no, it's going to be, we'll have to think about that. I have to build the table. Let's look at a graph before we build the table, because it helps us think about what the values are that are close to 2. If I move just to the left of 2, I'm getting numbers between negative 3 and negative 2, so it should be, let's say, negative 3, negative 2.5, negative 2.9, negative 2.99. So the 0.99s are going to be to the left, and the 0.01s are going to be to the right, like they were before. Let's draw a graph of this thing. The calculator's already set up for it. I can see the function right here, so let's go to y equals. And y equals is going to be 3x plus 2 in the numerator. And it's going to be 2x plus 4 in the denominator. And this time I'm going to start out like I did before. I'm going to go to the zoom window. I'm going to go down to zoom decimal. And I can sort of see what's going to happen when I go to zoom decimal, because I see that it's got the wings This is what's actually called a rational function. Rational functions always make these curves, where one goes up and the other one comes from the bottom and goes out to the right. Or sometimes it's where one of them goes down and the other one comes to the top and goes to the right. Rational functions are trying to avoid where they're undefined. This window is not as useful as I wish it was, so I'm going to hit the window button. And as I'm showing you here on the PowerPoint, I'm going to change that, but I'm just going to do it with multiplication. I'm going to multiply this times 2, and I'm going to multiply this value times 2, because I'm just trying to make the window twice as big. The only thing I'm changing are the min and max values. Now, since I'm trying to make it, actually this I want to make it about 3 times as big. So I'm going to multiply this times 3, and this one times 3. Simply because I know that this is really close to a negative 10 to 10 window. But it still has those decimals, so that when I trace, I can trace on decimal numbers. So when I look at the graph, you see that it looks kind of like that one. Now mine actually is still not connected. The graph on this actually is still in connected mode. If I go back to mode and change it to connected, there's the graph that I see. So whether it's dot or connected, and this one doesn't matter. Why is it acting so funny right here? Why is it behaving strangely right there? That's where the function's not defined. So something different happens when it's less than negative 2 from what happens when it's greater than negative 2. The whole function behaves differently. And in fact, if I go to my table and I do what I've done before, I'm going to start out at negative, let's see, we'll start out from the negative side first. Let's start out at negative 2.1. And negative 2.01 and negative 2.001 and negative 2.1231, which it translates to be negative 2, even though it really isn't quite at negative 2 yet. What's happening to y? Is it getting closer and closer to something? Infinity. Yeah, it's getting bigger and bigger and bigger and bigger and bigger. Okay, let's try going from the other direction. Let's see, on the other side I might go to like negative 1.9. And then to negative 1.99. And then to negative 1.999. So what's happening is I go from negative, the negative side, actually it's still negative, but it's from the right side because all those numbers are bigger than negative 2. So I'm trying to close it on negative 2 from the other side. What's happening to my y values? Are they converging to a number? No. No, if I come in from the left, I'm going to infinity. And if I come at it from the right, I'm going to negative infinity. Does infinity equal negative infinity? No. So does the limit exist at x equals negative 2? No. It's not because the function's not defined at -2. Remember, it wasn't defined at 2 in a couple of the ones we did before, and yet the limit still existed. But in this case, it's not defined at -2, but that's not the problem. What's the problem? The limits are going, and takes a lot more coordination than I've got. They're going like this. They're not coming like this. They're moving away from each other. Going down, going up, okay? Your left-hand limit does not equal your right-hand limit. Therefore, the limit does not exist. That's all that's required for a limit to exist, is that if you come at it from the left and you come at it from the right, they have to meet. Even though they might not quite touch, because that value that you're sneaking up on might not even be in the function's domain. But as long as they're equal, it's okay. It's all good. So, since the limit as x approaches -2 from the left increases without bound, we say the limit as x approaches -2 from the negative side of f of x is equal to infinity. And the limit as x approaches -2 from the right decreases without bound, then we say that the limit as x approaches -2 from the positive side is equal to negative infinity. I've already given Trina her headache.
Yeah. And as far as filling in those blanks, I don't have a clue from that on this paper that we have.
Okay, hang on, let me go back and, okay. If we graph it, we see that as the value of x approaches -2 from the left, the value of y approaches infinity. However, if we have the value of x approach -2 from the right, the value of y approaches negative infinity. This is because the function f of x has an asymptote. That's the actual math word. It has an asymptote at x equals -2, and that the function y has an asymptote. Its asymptote is at 3/2. Okay? It doesn't matter what y's asymptote is particularly, it's just that it does have an asymptote. So the limit as x approaches 2 from the negative side is positive infinity. And the limit as x approaches -2 from the positive side is negative infinity. And it says h of 2, but that should be f of 2, sorry, is undefined. And the limit as x approaches -2 of f of x does not exist, because those two are not equal. Does not equal or a does not equal sign goes in that last blank. Okay? Now I'm going to go ahead and page on down in case we need to come back. So example 5 is going to have an absolute value function in it. Okay, new function. Find the limit as x approaches 0 of the absolute value of x over x. Now, x can be positive and x can be negative, but what happens when you take the absolute value of x? It's going to come out positive, right? So if I were talking about x being -1, for example, that would be the absolute value of -1 over -1, And that answer would be -1. If I was plugging in -2, that would be the absolute value of -2 over -2, and 2 over 2 is 1, but the negative sign means it's -1. So as we get closer and closer to 0, there's no change. To the left of 0, the absolute value of x over x always comes out to be -1. Because it's a number over itself, but the denominator is always negative and the numerator is always positive. So it's always going to be -1. Now, if you're talking about positive values of x, the absolute value of 1 over 1 is 1. And the absolute value of 2 over 2 is 1. And the absolute value of 10,000 over 10,000 is 1. So you're going to get a horizontal line that's just y equals 1. But what about if we tried to plug in 0? 0's always been a troublemaker. What's the absolute value of 0? 0. And what is 0 over 0? It isn't 1. Unlike everything else, it isn't 1. That's the only number that you can't put over itself and get 1, because you're not allowed to divide by 0. I don't care what's in the numerator. Division by 0 is undefined. It's part of the 10 Commandments. Thou shalt not divide by 0. It is. It's the 10 Commandments of math. Thou shalt not divide by 0. A black hole is where God divided by 0. God can do it. We can't. Okay? So if you're talking about limits, as you approach 0 from the left, what's the value of the function? What's the value of that function for all negative values of x? -1. Good. What's the value of that function for all positive values of x? 1. Does -1 equal 1? No. So the limit doesn't exist. The limit from the left doesn't equal the limit from the right. It doesn't exist. That's why the limit doesn't exist. Notice it has nothing to do with the fact that the function's not defined at 0. It's not because that function is not defined at 0. It's because the limit, as you come at it from both sides, do not equal each other. You get two different values. So basically, this is the rules, and I'm going to put them again in English. If f of x becomes infinitely large in magnitude, positive or negative, as x approaches any number a from either side, we say that it either approaches infinity or negative infinity, depending on whether it goes up or it goes down. If x becomes infinitely not large as x approaches a from one side, and infinitely negative and large, I guess is the best way to say that, as it approaches from the other side, since it's approaching positive infinity and negative infinity, trying to approach that number, the limit doesn't exist. If the limit as x approaches any number, that's what a is for, is any number, from the negative side is equal to L, and the limit as x approaches a from the positive side is equal to m, and L doesn't equal m. In other words, if the left-hand limit doesn't equal the right-hand limit, then the limit of f of x doesn't exist at that number. Your limits have to match from the left and right. That's the moral of all of the first section. The limits have to match, or they don't exist. So just for kind of like a little wrap up here, looking at this crazy, wild, weird function that we have no equation for. This does not exist at -6, because from the left of -6 it goes to positive infinity, but from the right of -6 it goes to negative infinity. So that limit doesn't exist. The limit doesn't exist at -4. Because at -4, if you approach